Chemistry students, greetings. This is Mr. Resentas, and I'm in chapter 9. We're talking about single replacement reactions today, different types of reactions, and how they categorize them, how they are defined as redox reactions, and why. So let's just, before we talk about single replacement, what are the other types of reactions? Well, the other types of reactions are combination, and combination is also referred to as synthesis reactions, and you should be able to see it in word form. Calcium plus oxygen will combine to form calcium oxide. So you should be able to see this in word form and immediately think, okay, I have calcium, that symbol's simple enough, oxygen, that's simple enough, and calcium oxide, that's simple enough, calcium oxide. Well, oxygen, you know, is diatomic. Oxygen's diatomic, but what that does is that throws the balance off, so you'll also know that you have to take the next step, determine which is diatomic, and then the next step is to balance it. And in order to balance it, I'm going to need to add these coefficients. So, do I need to add a subscript? You might ask yourself. Well, in order to answer that question, you get the oxidation numbers, and the oxidation number of calcium is +2. The oxidation of oxygen is -2. How do I know that? I looked it up on my periodic table. Also, oxygen needs 2 electrons to become noble gas. That's another reason. That's another way to determine its oxidation number. Calcium has a little oxidation, so you could look at it's in group 2. It wants to lose 2 electrons, and so simple enough. This is a marriage made in heaven, because this one wants to accept 2 electrons, and this one wants to give up 2 electrons, and so we don't need any subscripts because their oxidation numbers are 0. Another thing I want to point out is why is this an oxidation reduction, and what do those terms mean? Well, calcium, as it sits by itself, has got to have an oxidation number of 0. I mean, it's by itself, so just like this oxidation number is 0, calcium oxide. This has to have an oxidation number of 0, and that's why it requires heat in order to get the reaction to go. And when we make the reaction go, because we've added heat, as you could see, it has an oxidation number of +2. So that means that it gave up 2 electrons, right? And so when it does that, it is oxidized. And the oxygen, it accepted 2 electrons, so we say that it is reduced, right? So what you have to just put to memory is oxidation, loss of electrons, reduction, gain of electrons. Right, another category of a reaction is the decomposition. The decomposition reaction, you should be able to take it in word form, like calcium, CalCium, calcium carbonate. Right, calcium carbonate will break down into calcium oxide and carbon dioxide. Right? You see this, and you think you'll have your periodic table handy, and you'll also have your list of polyatomic ions to find the carbonate, and so you'll write CaCO3 because you looked this up in your polyatomic ion list. and then you write this out in formula format instead of Word. And you think to yourself, okay, is this balanced? And then you think to yourself, do I need to add any subscripts? Do I need to add any coefficients? And am I finished here? Well, calcium has a +2, -2 for the carbonate, so that's fine. Calcium has a +2 and oxygen has a -2, so I don't need any subscripts here, do I? And then carbon has a -4, oxygen has a -2, so that's why we need 2 of them in order to get an oxidation number of 0, so I'm okay. Do I need to balance this? Do I need any coefficients? Well, 2 plus 1 is 3 oxygens. We have 3 oxygens here. We have 1 carbon here, 1 carbon here, calcium. So I'm balanced. I'm ready to move on. All right, so remember, you need to be able to go from word form to formula form, and if it's a decomposition reaction, I should also be able to just give you the reactant, and you predict the products. All right. Well, anyway, the last type of reaction that I wanted to talk about are the single replacement reactions. This is really what I was concerned about, the single replacement reaction. All right. So our first single replacement reaction, as I said, you want to start with the reactants and be able to predict the products, right? Well, our first is, by definition, if it's a replacement reaction, you're thinking to yourself, okay, iron is going to replace what over here, and how do you know what it's going to replace? And that's the question you're asking yourself. And one way you know is that you have this activity series. This activity series is listed in your chapter. You'll find it on page 295, or you could also I'll print this out for you. You can have it to put into your lab book. Now, in this situation, you'll see, what we're going to have is the metals replacing themselves for the most part. And in this case, the hydrogen is acting like the metal. All right. And hydrogen is lower on the activity series than iron. See, iron is more active. See how it says most? It's more reactive than hydrogen. So that means it's going to replace it. All right? Now, easy enough. All I've done was I've replaced the iron with the hydrogen, right? Well, when you're done, you think to yourself, okay, is hydrogen a diatomic? Yes, it is. So you're going to have to add that subscript. Also, you're going to have to think to yourself, all right, what is the oxidation number of this of chlorine? And so if you look, the oxidation of chlorine is -1. All right. So if the oxidation of chlorine is -1 and the oxidation number of iron is +2, then you're going to need 2 of these chlorines. All right. Now, in the here we have hydrogen is +1, and then Fe has got to be 0 because it's all by itself. It's just iron. It's iron in a solid form, I presume. All right, and then this must be hydrochloric acid in a liquid form, in an aqueous solution. So if we go back and try and determine what is oxidized and reduced, iron is oxidized. It's oxidized by the it gave up 2 electrons, and that is our definition. It's oxidation means loss of electrons. It gave up 2 electrons, and the hydrogen. Now the hydrogen, we know that it's diatomic, so there's going to be 2 of them. So we should just go ahead and just add put 2 the coefficient 2. So see, it's -1 here, and then it becomes 0 after the reaction. All right, because it's by itself. It has to have a 0 oxidation number if it's by itself. So we have it would have then gained electrons. Okay? So it's reduced. Okay? Chlorine -1, chlorine -1, and because it's unchanged, we call that a spectator ion. All right. So if I ask you which is the spectator ion in this reaction, which one has been reduced, which is oxidized, you should be able to identify those. Okay. Now in this next reaction, let's try another. So magnesium and copper sulfate. So we have this another polyatomic ion. We could look that up on our our little table. So this is a single replacement reaction. So we're replacing all we're doing is replacing a more reactive metal with a less reactive metal. See, copper is way down here. Copper is way down here on the reactivity series. Magnesium is way up here, so it's much more reactive. So it's going to replace. So all we're doing is we're replacing it, these metals, and we're replacing it with magnesium. I apologize. I'm looking at another problem. All right. So magnesium, as it's by itself, has a oxidation number of just 0 if it's all by itself. Copper is going to be +2. And then the sulfate is -2, so its oxidation numbers are 0. Magnesium is +2, sulfate is -2, as we just said, and then copper is going to have an oxidation number of 0. So magnesium then would have had to have given up the electrons. So it's oxidized. And the copper would have gained electrons. It's reduced by the oxygen as the oxidizer, and then SO4 is the spectator because there's no change. Right. And we could do the same thing. We could do the same thing with iron and copper sulfate. We could do the exact same thing because if we look on our activity series, iron is more reactive than is copper, so it's going to replace it. And so that's how you know that this reaction will go, or if it won't go. And so what will happen is the iron is just going to replace that copper, is all that's going to happen. And that, by definition, is a single replacement reaction. And you can determine which is reduced and which is oxidized. All right? So we're going to have FeSO4 plus Cu, just as we had a second ago. So we can say that Fe give up electrons because it's a positively charged ion, and so it's oxidized, and the copper would have gained electrons, and so it's reduced. And then SO4, just as a second ago, as I explained up here, is a spectator. It's a spectator because it's unchained.